Thanks, Ilya. So the next presenter is Patrizio Giovanni Notti. Yeah, he is a first-year PhD student at Royal Holloway and works as a data scientist for Centrica. Actually, last year he has studied and presented how to apply conformal prediction to email analysis. So this year he's going to talk about a transformer conformal predictor for paraphrase detection. Okay, can you share your screen?
Should be able to do that.
Yeah, great. Yeah, over to you. Yeah.
Right. Yeah, thanks, Yuan. Yeah, so in this work, I have applied inductive conformal prediction to a branch of natural language processing called paraphrase detection, where the task is essentially to recognize semantically equivalent sentences. So if two sentences have the same meaning, basically. I wanted to see if we can do it reliably. So if we can kind of have some sort of confidence measure on the predictions. There's a nice data set, which is the Microsoft Research Paraphrase Corpus. It's been published in 2005, and it's almost 6,000 examples, but each example is a pair of sentences, S1 and S2, and they are labeled as 1 if S1 is a paraphrase of S2, otherwise it's 0. So it's a binary classification task. And the class balance, so it's not, the data set is not really balanced in terms of classes. It's almost 70% positive examples. The general approach is to concatenate sentence 1 and sentence 2, separated by a special word, special token, and feed that kind of that object to the classifier. The current state of the art is given by transformers, which are a particular kind of neural networks based on attention mechanism. And they can be pre-trained on a large amount of text in an unsupervised way. And then you can use those pre-trained models and instead of training from scratch, your neural network, you can use the pre-trained model, start from there, from that, and fine-tune the model on your particular data set. So that's the approach, and they're also very efficient in terms of because they're very well parallelizable on GPUs. So BERT is the most popular pre-trained language model. It's been published by Google 2 years ago. And there's a version called DistilBERT, which is obtained by a knowledge distillation. It's basically a lighter version of BERT, and it's a bit cheaper to run. And especially it runs on my laptop GPU as well. So that was the necessary choice. And so we're using DistilBERT as an underlying algorithm. So for nonconformity measures, I've chosen 2 simple nonconformity measures. One is basically, if I take the probability outputted by DistilBERT, then I take minus that probability for each of the classes. And the probability is obtained by applying the softmax function to the last layer of the network, so that you transform the output into a probability distribution. So that's the first one. And the second nonconformity measure is taken by, so we can extract a vector, 768 dimensional vector from the last layer of the transformer, and that particular embedding can represent the entire sentence pair. So if we do this for all of the examples, and then we calculate the centroids, or the average embeddings for each of the classes, then we can take the Euclidean distance of each example to the centroid for each classes, and calculate, and use that distance as the nonconformity measure. So that's a more kind of geometrical approach. So we trained DistilBERT on our MRPC dataset for 5 epochs, and I am comparing the results with the normal DistilBERT original and DistilBERT with the 2 nonconformity measures. We see that the first nonconformity measure retains almost fully the accuracy, the predictive performance, just the F1 score goes down a bit. The second one is not as precise. And I've also calculated the observed fuzziness as a way to, to see how tight the prediction regions were. And even in this case, the first non-conformity measure gives a bit sharper predictions. In terms of validity, even if, I mean, I'm not sure about the independent, like if the examples were IIT in this data set, still we were able to control the error rate, while the calibration, so this is a reliability diagram for class 1, for the positive class, and we can see that the original Distilbert was very poorly calibrated, so it had good results, but very unreliable confidence estimates. Our implementation, it's much better. It's still not perfect. And the reason, there's many reasons. I think one reason is that my calibration set was tiny, as was just 10% of the training set. And this choice was because I wanted just to be consistent with the literature where some training validation test splits were already available. So I wanted to be able to compare results to the state of the art. So calibration set, was just 400 examples out of 4,000. And also, of course, their classes are a bit skewed. So I think that's part of the reason. So I guess, in future, we can definitely try with different proportions, proper training set and calibration, and also maybe try different non-conformity measures, which can be a bit more sophisticated. And also use larger models, pre-trained models. And I also wanted to apply the same method to other GLUE tasks, where GLUE is a general language understanding evaluation benchmark. So it's a group of like 8 data sets that you can use to benchmark your algorithm for language understanding. So it would be nice to see how this approach generalizes to other tasks. And if we can still provide a good reliability for the predictions. And that's it. I don't know if there's any question.
Yeah, thank you. Yeah. Excellent. Yeah. Any question, comment?
Just out of curiosity, how imbalanced is the data set to start off with?
So it's basically, I think it's 68% positive and 32 negative. So it's fairly balanced.
I have the following question. Okay.
Oh yeah.
BERT and Distilbert, it's mostly embedded, which we usually use for transfer learning to last layer and to final training for model. Okay.
Yeah.
So what I'm confused with is the second column when you say probability of label. Distilbert. So you use Distilbert, and after that you additional train on this corpus, or what? Where you get this probability?
Yeah, so so there's a pre-trained model, so which has been pre-trained on a lot.
This is called BERT and Distilbert. This is a pre-trained model. Yeah.
Yeah, that's Distilbert. Then you can use the same network with these weights.
Yeah.
A new training with your with MRPC data, with my data set in particular.
So it means that just to check that when you say probability O output of layer Distilbert, it's not real Distilbert, that you use Distilbert, and after that you additionally train on your data.
Yeah, you're right. Yeah, this is the output of the fine-tuned Distilbert. So
okay,
the second training phase, then that's the probability.
Yeah, it would be much better to put key and sentence layer of 5-tuner Distilbert. Yes.
Yeah, absolutely.
Okay, thanks. And the same probably when you use about the second measure, you don't need pre-training, or did you use? You also need some pre-training, or what?
Yeah, you could. I mean, you could either. I thought I could use the pre-trained version without having to fine-tune, But then I saw a comment online by the creator of BERT that said, no, if you want to use the last layer as embedding for the sentence, then you need to fine tune it first. And then also after the fine tuning, you can get the representation from the last layer.
Okay. And the last question, because you need mostly just in all these tools, you just need embedding. And after that, you play with embedding, just pre-train. So my question is, apart of course, transformer is a sexiest topic in natural language processing, yes?
Yeah.
But there are much simpler and great so-called, for example, on the same Google web page, when you have model on BERT and this one, there is called universal sentence embedding, which I like very much. It doesn't give you 700 something or 500 something embedding. It's built on this one, and it's very fast on this one. So, so my question is, have you used some sort of specific of BERT, or you just need embedding, and after that you just?
No, I read about universal.
So what's the reason about this? So what is so important about just transformer and not just universal embedding or whatever?
I think one of the main reasons was because there is this leaderboard, where you can see all the performance of the competing models, and they're all transformers basically. And I wanted to see.
Yeah, I agree. Yeah, this is what I thought. As I said, it's the most sexy words now in natural language processing. Yes.
Yeah, but definitely, we could use actually, maybe simpler methods and like.
No, but you know what will be interesting is, for example, when you use universal encoding, which is different, and finally it perform better than this heavy BERT. But this will be nice. This will be something, unexpected. Okay.
Yeah, I should try that. Thanks.
It's nice. I'm more impressed when some sort of simple, beautiful method perform better than this heavy, everybody uses it. So it needed something unusual, yeah. Thank you.
Yeah, I think that's a starting point. Then definitely move to something more, elegant.
Mm-hmm.
Thank you. Yeah. Any more questions? Maybe I can ask a question. So actually, you can take the last layout as a feature to put into any machine learning algorithm, right? So
yeah. So what
have you compared or do get similar kind of performance to use trained BERT model?
No, I didn't, because I think because everything it was already ready in a sense. Like once you have these embeddings, then once you use the implementation, it goes straight to the to the probabilities. You don't need to do further work. So I didn't try and and use the other algorithms with the embeddings. But yeah, in principle, you could just take these embeddings and train whatever classifier you want.
Okay, thank you.